Okay, hello bro. Back with me, Rannegoro. We are going to discuss about some classical mechanics, questions or problems at the undergraduate or postgraduate level. Problems that we will discuss is related to Newton's second law with the projectile motion or parabolic path equation phenomenon. Okay, prepare yourself to enter the world of classical mechanics. This is the first problem. A cannon, when aimed vertically, is observed to fire a ball to a maximum height of L. Another ball is then fired with the same speed, but with the cannon aimed up along a plane of length L, inclined at an angle theta, as shown in figure. So this is the theta. And what should theta be so that the ball travels the largest horizontal distance, d, by the time it returns to the height of the top of the plane? Okay, let's solve this problem. First, we can get the initial speed by the form of parabolic equation. Okay, so we can write it as Vt square equals to Vo square minus 2gl. And we can substitute Vt with a 0 and we get the value of Vo equals square root of 2gl, where L equals Vo square divided by 2g. Imagine dropping the ball from the maximum height and we can get some equation. L equals Vot plus 1/2 gt square, and we can substitute the Vo equals 0. This is the free fall motion, and we can get L equals 1/2 gt square, and V, the last speed, equals gt. This is the sum equation by the free fall of the ball approach. Okay, the next, when the ball is fired up the plane, the acceleration along the plane is minus g sin theta. This is the acceleration along the plane. Along the plane. Yeah, so the position along the plane is, with the function of t, equals Vot plus 1/2 a t square, and we can substitute ta with the minus g sin theta, so we can get like this. And setting this equal to L gives, this is the substitution of L, and we can get some equation, of course. The first, we can write Vt square is equals to Vo square minus 2g sin theta L, and Vt equals Vo minus g sin theta t, and we can substitute this. Vt square is same with Vt equals square root of this term. Okay, the left side of this equation we substitute by square root of Vo square minus 2g sin theta L. The right side is the same term, Vo minus g sin theta t, and we can move this term to the left side and we can get equation like this. This term is from the left side, Vo square minus 2g sin theta L. Okay, and we can get the t value with moving g sin theta. We can get Vo minus square root of Vo square minus 2g sin theta L divided by g sin theta. Okay, and the speed at the top of the plane is then, and the speed at the top of the plane. The speed at the top of the plane we can write as Vt Vo minus g sine theta t, and we can write it as the square root of Vo square minus 2g sine theta L, and we can using the value of Vo above in this term. Okay, we can substitute this. Vt equals square root of 2gl square minus 2g sine theta L, and we can change this form by the factorize 2gl, and we can get like this. And the range of the resulting projectile motion is the usual, and we can write the range as d equals Vt cos theta to Tp, where is Tp is the time to the upward motion, and we can write Tp as a equation like this, Vty, and we can get T equals Vty divided by g, and Vty is the vector as an upward direction, so Vty is sine theta divided by g. Okay, and this equation we can change by the substitution with the Vt cos theta to Vt sine theta divided by g, and we can get d equals 2 Vt cos theta sine theta divided by g. This is the usual form of the range of the resulting projectile motion, and this equals to d equals 2 square root of, by the substituting of the Vo, 2gl 1 minus sine theta. Of course, this is the square cos theta times sine theta divided by g, and we can simply this equation with 2 get outside of the square root of this term, and we can get 4gl plus times 1 minus sine theta times cos theta times sine theta divided by g, and we can erase g, so is equals to 4l times 1 minus sine theta times cos theta times sine theta. This is the range of the resulting projectile motion. Taking the derivative and using identity of trigonometry and give the derivative of d, okay, like this. So by the some partial method, we can get for L with the constant value, we can get outside of the bracket, and okay, this system is the derivative of d cos theta square minus 2 sine theta cos theta square plus sine theta square times minus sine theta. Okay, and we can get the maximum and minimum of d when d of derivative of d equals 0. So we can substitute this term by 4l times minus sine theta square plus cos theta square minus 2 sine theta times 1 sine theta square minus sine theta cube. And we can move this term to the right side, so the yield is 0. Simply of this equation, we can get 3 sine cube theta minus 2 sine theta square minus 2 sine theta plus 1. By the factorize of this cube equation, we can get sine theta minus 1 times 3 sine theta square plus sine theta minus 1 equals 0. Of course, this term sine theta equals 1, so theta a half of b. This is the minimum value of t, of course. Fortunately, the remaining quadratic yields a positive root of sine theta is minus b plus minus square root of b square minus 4ac divided by 2a, and substitute by the coefficient of term b is equals minus 1 plus minus square root of 1, of course, 4 times 3 times minus 1, and divide by 2, 3. So we get sine d equals minus 1 plus minus square root of 3 divided by 6. Numeric value of theta calculated by the computer, we get value theta is equals to 25.7 degree. This is term when square root of 3 is minus. Okay, like this. Let's move to the second problem. A plane is inclined at an angle theta below the horizontal. A person throws a ball with speed VO from the surface of the plane. How far down along the plane does the ball hit if the person throws the ball? A. The conditions are perpendicular to the plane, and B. horizontally. Of course, by some projectile motion equation, we can solve this problem. Okay, let's solve these problems. First is the A condition. Looking at the direction perpendicular to the plane, the initial speed is VO, and the acceleration is, of course, g cos theta. So first, we can illustrate this condition like this. This is the ball with the acceleration downward is g. So this is the acceleration parallel with the plane is g sine theta, and perpendicular is g cos theta. So the acceleration is backward to the plane. This is the v, and of course this is the theta with the theta. And this is the theta. So this is Vy and Vx. Okay, so we get equation Vy equals Vo minus g cos theta times t. Velocity at the top, x equals 0. So this is the different thing from, this is the velocity at the top when we have a reference of the direction motion is this. Okay, so Vo minus g cos theta times t. And we can get t equals Vo divided by g cos theta, and t at the total time in the air is equal to 2 times t. So we can put index of t 1, and t the total time, of course, equals to 2 Vo divided by g cos theta. We save it. Okay, and the horizontal speed of the ball is always Vx equals Vo sine theta. Vx equals Vo sine theta. So the x value when it hits the plane is x Vx t. So we can substitute Vx by Vo sine theta times 2 Vo divided by g cos theta, and the distance down along the plane is then t x divided by cos theta. This equation is from this illustration theta, so x like this, x divided by cos theta. Okay, and we can substitute the x by Vo sine theta times 2 Vo divided by g cos theta divided by cos theta. And t, of course, 2 Vo square sine theta divided by g cos theta square. We save it. If theta is equals 0, then t equals 0 as expectation of this term. If theta equals 90 degree, then d is equals infinity value as expected. Note that we could have instead found the time by demanding minus tan theta equals y divided by x equals, of course, substitution. We get gt squared divided by 2 divided by VO sine theta times d. So by the identity of trigonometry, tan theta is equals minus sine theta divided by cos theta, and this term is same with this, so we can write like this, and we can move this term to the left side, and we can get VO minus VO sine square theta divided by cos theta times d. And the right side is VO cos theta times d minus 1/2 gt square. So we can erase or simply this equation by remove t, and we can get 1/2 gt square by moving this term to the left side, and VO cos theta. So we can compile this term, and we can get VO in the bracket cos theta plus sine theta square divided by cos theta, like this. So t equals 2 VO divided by g times cos theta square plus sine theta square divided by cos theta. And we can simply this term by the identity of trigonometry, where this is equals to 1, and so that t equals 2 VO divided by g cos theta, like this. Okay, this is the how far and the times where the person throws the ball perpendicular to the plane. And so the horizontally throws is identical to the perpendicular to the plane condition. You can try to solve this problem by yourself. Let's move to the next problem. A cart is held at rest on an inclined plane. A tube is positioned in the cart with its axis perpendicular to the plane. The cart is released, and at some later time, a ball is fired from the tube. Will the ball eventually land back in the tube? Hint: choose your coordinate system wisely. Okay. We can solve this problem by some approach like this. Yes, the ball will land back in the tube, and we can solve this problem by working the horizontal and vertical axis, of course, which involves finding the intersection of the parabolic projectile motion and the inclined plane. But it gets rather messy. So let's use the tilt axis parallel and perpendicular to the plane, which yields a quick solution. If v is the component of the cart's velocity along the plane when the ball is in a fired, then the position of the cart along the plane relative to where the ball is fired is Vt plus 1/2 g sine theta times t square. This is the position of the cart along the plane. But this is also the coordinate of the ball along the plane, because the ball's initial speed along the plane is likewise v. Of course, because the tube is perpendicular to the plane at all times. So the ball lands back in the tube. In short, we have two true statements concerning the direction along the plane. First, the ball and cart have the same initial velocity and always the same a g sine theta. This is acceleration. So they always have the same velocity. And second, the ball and cart have the same initial position and always the same v, of course, due to the GabutBerFis statement, so they always have the same position. Okay, this is the solution of third problem. Okay, and now let's move to the fourth problem. A hill is sloped downward at an angle beta with respect to the horizontal. A projectile is fired with an initial velocity perpendicular to the hill. When it eventually lands on the hill, let its velocity make an angle theta with respect to the horizontal. And what is theta? And what beta yields the minimum value of theta? And what is this minimum theta? Okay, let's solve this problem. First, consider the direction perpendicular to the plane. The acceleration is g cos beta back toward the plane. So if the initial speed is v, okay, first we can illustrate as the pole with a v in this direction. So of course the pole is have g acceleration to downward, and we can spare it this vector to g sine beta. Of course this is beta angle, and this is g cos beta. And of course the path of the pole is like this. Okay, and we can have theta on this. Okay, respect to the horizontal, of course. And we can solve this problem by first equation is Vt equals V minus G sine B TO. Oh, sorry, this is cos. Okay, so TO is V divided by G cos beta. At the R, the total times is T equals 2 TO, and T of course 2V divided by G cos beta. Okay, we save it. Okay, of course we can have the vector part of the V like this with the horizontal direction, of course Vx, and the vertical direction is Vy. Of course this is beta, and we can spare it vector of V by the trigonometry value. This can also be obtained by demanding that minus tan beta equals y, of course as function of t, and x a function of t. And tan theta, of course, is by identity of trigonometry is equals sine beta divided by cos beta. And we can write y as a function of t is equals vy t minus 1/2 gt square divided by vx t, and of course equals minus tan beta by the trigonometry value. Vy is equals v cos beta times t minus 1/2 gt square divided by v sine beta times t, and we can substitute this by sine beta divided by cos beta. Okay, and we can move this term to right side, and we get v cos beta minus 1/2 gt square equals to minus vo sine beta square divided by cos beta times t. We can compile the vo. Sorry, okay, this is the vo. Okay, vo, and we can get vo t in the bracket cos square beta, of course, by same denominator, sine beta. This is the denominator is cos beta. Of course, is equals to 1/2 gt square, and we can simplify this term by e raised to t. Of course, the t equals, this is the value of identity trigonometry, is 1, and t equals to v divided by g cos beta. Okay, we save it. When the projectile hits the plane, we have, using the both value of t, of course the tan theta, value of velocity, okay, like this. And we can write v dot is equals to vy minus gt. Okay, this is absolute value. So the x, of course, v sine beta. We can move vy to behind v sine beta. Of course, we can substitute vy, and of course t equals to 2v divided by g cos theta. This is the g, okay, minus vy is equals to v cos beta divided by, okay, we can of course divide by v sine beta, and we can simply this term by multiply 1 divided by v. Of course, we get tan theta equals 2 divided by sine beta cos beta minus cos beta divided by sine beta, and we can substitute this term by the identity of trigonometry. So we get 4 sine 2 beta cot tan beta, okay, and setting the derivative of this equals 0. Of course, to obtain minimum value of v of theta, and we get d tan theta divided by db by the partial derivation. Of course, 0, the first term, minus 4 times 2 cos 2 beta divided by sine 2 beta square minus cos sec second beta cosec beta square equals 0, and we can move cosec beta square to the right side, and we get minus 8 cos 2 beta divided by sine 2 beta square equals to minus cosec beta square. Of course, the sine minus we can remove, and 1 divided by sine square beta, and this is y cos 2 beta divided by sine 2 beta square, and we can change this term by the identity of trigonometry. So we get cos 2 beta divided by 4 sine beta square times cos beta square is equals to 1 sine beta square. We can remove this, and we get 2 cos 2 beta equals cos beta square, and we can move this term to left side. We get, of course, we can change this term by identity of trigonometry to beta minus 1 minus cos beta square equals 0. We get 4 cos beta square minus 2 minus cos beta square, and we get 3 cos beta square equals, we can move this term to the right side, equals 2, of course, and cos beta square is equals to 2 divided by 3, and cos beta equals square root of 2 divided by 3, and by the numeric method we get beta with the approach solution, we get 35.26 degree. Okay, and also we can take the triangle approach with the angle beta like this. So cos beta is equals to square root of 2 divided by square root of 3. So this side with the p value is equals to square root of 3 minus 2 is equals to 1. So the tan beta equals to 1 divided by square root of 2, and the sine beta is equals 1 divided by square root of 3. So tan theta is equals 2 divided by sine beta cos beta minus cos beta and sine beta, and we can substitute the trigonometry value like this. Sine beta is equals 1 divided by square root of 3, and this is square root of 3 divided by square root of 3, square root of 2 divided by square root of 3 minus square root of 2 divided by square root of 3, and 1 divided by square root of 3. Of course, we get 2 divided by square root of 2, of course, and divided by 3 minus square root of 2 with the simply value, and we can get tan theta is equals 6 divided by square root of 2, and square root of 2 as the minus as the subtraction. So by the rational number we get 3 square root of 2 minus square root of 2, and tan theta at the last, and the simplification is 2 square root of 2, and the associated theta is given by the tan theta. So we get theta with the numerical value approach is equals to 70.5 degree. Okay, like this. Okay, now we move to the next problem. What is the maximum angle at which you can throw a ball so that its distance from you never decreases during its flight? You never decreases during its flight. And B, this maximum angle equals the minimum theta from exercise number 4 before, and explain why this is true. It is necessary to have done that exercise. Okay, let's move this problem. Of course, this problem can solve by some identical equation with the fourth problem. Okay, the A problem. Since x equals v cos theta times t, and y v sin theta times t minus 1/2 gt square, the square of the distance from you is like this. Okay, of course this is the constant value, never decreases during the flight, and we can substitute the x and the y by v cos theta times t square plus v sin theta t minus 1/2 gt square, and we get like this, square square of course, and this is the square sin theta square times t square. Okay, square, and we can do 1/2 v 1/2 v sin theta 3 cube and plus 1/4 g square t to the 4. Otherwise, by identity of trigonometry, this is the cos theta square and this is the sin theta square. We can get 1 and we get v square t square minus vg sin t cube plus 1/4 g square t to the 4. Okay, this is the L square. And we want derivative of L, just L square, to never be less than 0. 0 equals 2v square t minus 3vg sin theta. This is the multiplication. T square plus g square t cube. Of course, divide by t, the all of term, we get 2v square minus 3v times g times sin theta t plus g square t square. Okay, by the quadratic solution, we get t equals minus b plus minus b square minus 4ac divided by 2a. And we can substitute the b by 3vg sin theta plus minus square root of 9 v square g square sin theta square minus 8 v square g square. And this all divided by 2g square. And the solution does not exist for t if the discriminant is 0. That is, if sin theta less than 2 square root of 2 divided by 3. Okay, sin theta less than 2 square root of 2 divided by 3. So that the theta is less than 70.5 degree. Okay, so if theta is less than or equal to 70.5 degree, then L never decreases during the flight. Okay. And where does this term come from? We can make some approach like this. This is the 9, this is the g sin theta square. Of course, this is the egg, this is the egg v square g square. And we can simply this term and we get sin theta square is bigger than egg. Okay, like this. Oh, sorry. This is not the is bigger than, is the less than. Okay, so this sin theta is less than, like this, 2 square root of 2 divided by 3. Okay, this is the form come from. Okay, this is the solution for equation, and let's move to the B question and let theta is equals. Okay, this is the B question. Let theta, this is the initial theta, is 70.5 degree. Okay, if you throw a ball at angle theta larger than the theta 0, then there is a point, actually the 2 point in the flight where dl dt is equals to 0. This means that at this point the ball is moving in the direction perpendicular to the radial line from u to the ball. So if this radial line is considered to be the slope of a hill, then the ball at this point has a velocity that is perpendicular to the hill. It has a velocity that is perpendicular to the hill. the time reverse motion of the ball, therefore satisfy the setup in exercise before. Conversely, if you throw a ball at an angle theta smaller than theta 0, then there does not exist a point where the ball is moving perpendicular to the radial line from you to the ball. So therefore, the velocity is never perpendicular to the slope of a hill, which means that such a theta isn't possible in the setup of exercise before, as we found. If someone claimed that they could produce an angle theta is less than theta 0 in exercise before, then the time reverse motion would yield an angle theta less than theta 0, for which the distance decreases at some point in the flight, namely just after the ball passes through the hill, in contradiction with the result of this problem. Okay, like that. Okay, let's move to the next number, the sixth problem. A ball is thrown with speed VO at an angle theta. Let the drag force from the air take the form Fd equals minus beta V, of course, with the approach m alpha V. And find xt and yt, and b, assume that the drag coefficient takes the value that makes the magnitude of the initial drag force equal to the weight of the ball. Okay. If your goal is to have x be as large as possible when y achieved at maximum value, you don't care what this maximum value actually is. Show that theta should satisfy sine theta equals square root of 5 minus 1 divided by 2, which just happens to be the inverse of the golden ratio. Okay, let's solve this problem. Okay, first the A problems. At A condition, we can first write the second law of like this. Of course, the F and the A is the vector quantity. Give some approach with the x double dot is equals minus alpha x dot and y double dot is equal minus g minus alpha y dot. Okay, this is the acceleration with the x direction and y direction. Using the initial speed, the x equation integrates to, okay, x double dot is minus alpha x dot, and we can write x double dot with the x dot dt is a minus alpha x dot. Okay, with the integral the x dot, okay, we can move x to the left side, and the right side is integral of minus alpha dt. Okay, this is L ln x dot minus alpha t plus c, and we get x dot with exponential by the logarithmic natural logarithm is equals to a minus alpha t plus c, and we can separate this term by t times a to the c. Of course, this is the constant value, so we can write x dot with a times e minus alpha t. We save it. When t equals 0, so that x dot equals VO cos theta, and x dot equals a times t to the minus alpha t. So at the t equals 0, with the x dot is VO cos theta, so a we get with equals to VO cos theta, and we can get x dot VO cos theta e to the minus alpha t. Okay, we save it. Assuming an initial position of 0, this then integrates to x dot VO cos e to the minus alpha t of course, by integrating value, integrating equation, cos theta e to the minus alpha t dt. So the x is equals minus 1 divided by alpha VO cos theta in the bracket, and e to the minus alpha t plus b, where b is the constant value. So we can take approach t equals 0 at the initial position is 0, so that minus 1 divided by alpha VO cos theta plus b, and b we get VO cos theta like this, and x is equals to minus 1 alpha VO cos theta e to the minus alpha t plus b, and we can substitute the b like this. This is a minus 1 alpha cos VO cos theta e to the minus alpha t plus this term like this, of course. So it's sorry, this is the plus sign. Okay, plus 1 alpha VO cos theta. So we can make a sum factorize and the multiplication for this equation. So we can get out from the bracket VO cos theta divided by alpha. So in the bracket is 1 minus e to the minus alpha t. This is the x as a function of t. And let's make a sum equation and sum function of y. First we can write y double dot equals to minus alpha g minus alpha y dot, which can be written as minus alpha in the bracket g divided by alpha plus y dot, and it can be integrated like this, the double dot, with the same approach with the x term like this, and the g divided by alpha plus y dot equals to minus alpha dt, and we get ln g divided by alpha plus y dot equals minus alpha t plus c. Of course, c is a constant value, so we can separate this with the g divided by alpha plus y dot equals e as a natural number to the minus alpha t plus c, and we can separate this by exponential approach. G alpha plus v dot is equals y to the minus alpha t times e to the c. Okay, we can write it as a constant a value, so we get y dot is equals a times e minus alpha t minus g divided by t, and y dot is equals a e to the minus alpha t, and with the substitution of a by the same approach to this condition, we can get VO sine theta plus g alpha. This is the a value minus g alpha. Sorry, this is the alpha, not the t. Okay, and we can integrate this term, of course, with the same approach. dy equals integral VO sine theta plus this, okay, e minus alpha t g alpha, of course, dt, like that. So y as a function of t is equals minus 1 alpha VO sine theta plus g divided by alpha e to the minus alpha t minus gt divided by alpha plus t. Of course, t is a constant value, and we can get this value with the approach of t equals 0 when t equals 0, so that the y is 0, and we get t equals 1 alpha VO sin theta plus g divided by alpha plus gt divided by alpha. Of course, this is the 0 value because the t value is 0, so that the y as a function of t is 1 alpha VO sin theta plus g divided by alpha 1 minus e to the minus alpha t minus gt divided by alpha. This term is from the substitution of t, and we can get some multiplication of this term. Okay, this is the simplification of t as of y as a function of t, like that. This is the solution for A question. Okay, let's move to the B question, that with assumption that the drag coefficient takes the value that makes the magnitude of the initial drag force equal to the weight of the ball. Okay, we can first by the equation of m alpha VO equals mg. This is the equation of the acceleration. So VO equals g divided by alpha. Therefore, equation gives y dot equals VO sin theta plus g divided by alpha e to the minus alpha t minus g divided by alpha. This comes from the term before. Okay, this comes from the term before. Okay, at the top, of course, y dot is 0, so we get VO sin theta plus g divided by alpha e to the minus alpha t minus g divided by alpha is equal 0. And we can move this term to the right side, and we get VO sin theta plus g divided by alpha times e to the minus alpha t equals g alpha. Okay, we can make some compilation of this term g divided by alpha with the same value of this. So VO sin theta plus VO in the bracket and the times e to the minus alpha t equals VO, of course, and we can simply this equation by dividing the VO by dividing with the VO. So we get sin theta plus 1 e minus alpha t 1. So we get e to the alpha t minus alpha t equals 1 sin theta plus 1. Okay, using equation on the process A, we get some x value. Using equation on the process A or A problems, we get x equals VO cos theta divided by alpha, of course, like this, and we can substitute the e, where e is equals 1 divided by sin theta plus 1. Okay, so x is VO square divided by g, with the cos is entered the bracket in the right, so we get the same denominator like this, sin theta plus 1 cos theta come from this term minus cos theta, and of course with this identity of trigonometry we get VO square divided by g sin theta cos theta divided by 1 plus sin theta. Okay, and we can substitute this term with the identity of trigonometry is equals to 1/2 sine 2 theta 1 plus sine theta. Okay, taking the derivative to maximize the x with the value of derivative is 0. Of course, we get to with the partial derivation 2 cos 2 theta times 1 plus sine theta minus sine 2 theta times cos theta divided by 1 plus sin theta, of course, equals 0. So we can erase this term, and we can erase this term with the moving to the right side, and we get 2 with the some identity of trigonometry 2 sine theta square. This substituting this term, this is 1 plus sine theta and minus, of course, this is can be written as 2 sine theta cos theta equals 0. This come from, okay, and we can get 2 minus 4 sine 2 theta with the 1 to this and sine to this. We get 4 minus 4 sine theta square, of course, plus 2 sine theta. This is the term, okay, and this is get 2 sine theta, whereas this is cos theta square, and we can substitute by 1 minus sine theta square, of course, equals 0, and we can simply this term by erasing this value, and so we get 2 minus 2 sine theta cube minus 4 sine theta square minus plus 1 plus 2, sorry, okay, and we can divide this term by minus 2, and we can get sine theta cube plus 2 sine theta square minus 1 equals 0. With the polynomial approach, we can take the Horner method like this. This is main the root, okay, so we get like this. This is minus 1, this is 1 plus, of course, 0, and we can get the root of this term, or the factor of this term is equals sine theta plus 1 sine theta square, this is the coefficient of this term, plus sine theta minus 1 equals 0. Of course, this is get the theta, sine theta equals minus 1. This is the value of the 270 degree, and this term we can solve by quadratic formula, where is sin theta is equals minus b plus minus square root of b square minus 4ac divided by 2a, and we can substitute b with the minus 1 plus minus, this is 1, 4a is 1, and c is minus 1, and 2 equal times 1, and we get minus 1 plus minus square root of 5 divided by 2. Okay, we get sine theta equals minus 1 plus minus square root of 5 divided by 2, and we take the plus sign at the square root of 5, so we get like this, and where theta is arcus sine square root of 5 minus 1 divided by 2. Of course, theta is equals, with the numeric approach, is equals to 38.2 degree. Okay, so that theta satisfy this is equals to 38.2 degree, like that. So this is the end of this video. More or less like that, the use of the parabolic motion equation to solve problem related to Newton's second law, and we can develop and apply it to the other case, of course. And thank you for your attention. Please, you can comment below if my delivery is not appropriate. Thank you again and see you soon. Salam dari kawanku.